Que salga por la
Sí, sí.
Okay. Good afternoon, everyone. Thank you for being here for our seminars of our cycle of seminars of the astronomy department. Today, we have the pleasure of having with us Professor Gustavo Romero, and I will briefly introduce Gustavo. He's a full professor of relativistic astrophysics at the University of La Plata, director of the Argentine Institute of Radioastronomy, and superior researcher at the National Scientific and Technical Research Council of Argentina. He's a former president of the Argentine Astronomical Society and has published over 500 papers on astrophysics, gravitation, cosmology, and the foundations of physics. He has authored or edited 13 books, and Dr. Romero has supervised more than 40 PhD and master theses. His current primary interests include high-energy astrophysics, black hole physics, space technology, and the scientific philosophy. So, Gustavo, whenever you are ready.
Ok, muito obrigado, María, por la presentación, por la invitación. Le voy a ver el switch para inglés ahora. Well, no, don't worry. Well, I'm going to talk about microquasar remnants, but perhaps it's better to start reviewing some basic concepts about microquasars. So I will spend a few minutes presenting what a microquasar is. Perhaps many of you know that microquasars are binary systems, systems formed by a star, normal star. It could be a high mass star or a low mass star, and a compact object. And there is a transfer of mass. Sorry? A porno? Cool. Okay. There is a transfer of mass from the star to the compact object. Since the mass has angular momentum, it forms a disk around the compact object, and this disk cools through emitting thermal radiation in the form of X-rays. So, in general, all microquasars are also X-ray binaries. But what is most characteristic of microquasars is the presence of two jets. Jets are very collimated beams of particles and fields that are ejected somehow from the surroundings of the black hole. Probably some magnetic mechanism such as Blandford-Snijek, or perhaps an hydromagnetic mechanism such as Blandford and Payne mechanism. These jets propagates through the interstellar medium and produce this type of structures in the interstellar medium. They resemble very much radio galaxies, if you see, with hot spots, jets, and a core. This is a radio image. Most of this radiation is non-thermal radiation, so these systems are capable of accelerated particles up to high energies, relativistic energies. And they used to present several spectral states. The two main states are these two, the so-called high soft X-ray spectrum, where you have a peak close to a 1 keV, and then this is more or less like a black body, and then you have a condensation feature and a power lobe tail. In the other state, most of the energy is at higher energies. The peak of the spectrum is around 150 kilo electron volts. And this is also condensation of soft photons. And there is also a high energy tail that in some cases could extend into the MeV range, gamma rays. Okay. These are some famous microquasars in our galaxy. Altogether, we know 25 of these objects in the galaxy, and several others in other galaxies. This is Cygnus X1, perhaps the most famous one. It was the first galactic black hole candidate in a binary system proposed in the 60s. And a jet has been detected with VLBI at radio wavelengths. It's not a very long jet at radio. It's a compact jet close to the compact object. This is another famous object, GRS 1915. It was the first superluminal source detected in the galaxy by Mirabel and Rodriguez in 1994. This also is a very well-known object, SS433. It's famous because the jets are precessing. You can see the helical pattern of the jets due to the precession in this radio image here. And this was the first microquasar discovered. It's very close to the galactic center. It's called the Great Annihilator because there is an electron-positron annihilation line coming from this system. So probably there is copious pair production in the jets of this object. And this is Cygnus X3. You can see the radio shed here, which is also famous because in the 80s there were many reports of extremely energetic radiation from this object. But these early reports were ruled out because of deficiencies in the detection techniques at the time. But as we will see, nowadays it was detected again. And regarding the classification of these objects, there are many proposals. They can be separated according to the mass of the donor star in high mass microquasar or low mass microquasars. Or, for instance, if the compact object is a black hole or a neutron star, or according to the spin of the black hole, high spin and low spin systems. But probably the most physical classification is the one that is based on the spectral states and the accretion regime. So let me say a few words about the accretion regimes of these systems. Essentially, you have three different accretion regimes according to the accretion rate onto the compact object. At very low accretion rates, this is the accretion rate, you have what is called an ADAF, or also a REAF. This is radiatively inefficient accretion flow. And ADAF is advective dominated accretion flow. So in this regime, the disk is optically thin, so it's transparent to its own radiation, but is geometrically thick. The inner part of the disk is inflated. And electrons here are extremely hot, and they can comptonize photons from the outer parts of the disk, producing this high energy tail that we saw in X-rays, in the LHAASO state. Then at medium accretion rates, we have the standard disk, which is usually modeled as in Sakura-Sunayev classical model. This disk is geometrically thin, but optically thick, so it's not transparent. And in the high soft state, it extends all the way up to the last stable orbit, close to the black hole. So this is the hotter part of the disk where most of the radiation is produced. And then if you surpass the Eddington limit, you will enter in another regime that is much less explored than the previous ones, which is the super Eddington regime or supercritical regime. And here the disk is extremely hot and is radiation dominated. The radiation inflates the disk, so these are also geometrically thick, but they are also optically thick. And in this regime, the accretion rate changes with the distance to the black hole. So the excess beyond of matter, beyond the Eddington limit, is expelled by radiation pressure from the surface of the disk. Actually, there is no surface of the disk. This disk is not stable and essentially is blowing up its outer parts. So in this case, you will always have this extremely powerful and dense wind expel radiation driven by the radiation from the accreting matter. So these are essentially the three regimes. And each regime has a characteristic spectrum or spectral energy distribution. This is for the low accretion rate with the peak at high energies. And this is the standard Sakura-Sunayev spectrum. Many sources used to switch between these two states according to what happened in the inner part of the disk. The inner part of the disk in the optically thick and geometrically thin disk model can break, and the fragments can form a kind of corona or inner part that becomes very hot. So the system can change from this state to this state and vice versa. And this is the radiation-dominated state. It's strongly dependent on the viewing angle. So if you view the system face on to the spin of the black hole, you will see through a funnel in the wind the radiation from the inner part, and you will have what is called an ultra-luminous X-ray source. But if you see from larger viewing angles the system, it will appear as a microquasar, but a very powerful one, such as SS433. And regarding the typical temperatures of the systems, for the supercritical regime, you will have around, for a black hole of 10 solar masses. Just an example, temperatures of the order of 10 to the 8 Kelvin. And then for the standard disk, you will have temperatures in the inner part between 10 to the 6 and 10 to the 7 Kelvin. So this will produce soft X-rays. And the ADAF will have extremely high temperatures for the electrons of the order of 1 billion Kelvin. Protons could have 1,000 times more temperature than the electrons in this system. So it's a two-temperature plasma. Okay. And also, depending on the accretion rate and the spin of the black holes, this system can produce these jets that I mentioned at the beginning. If you have a high spin and low accretion rate, so you have, for instance, an ADAF, you will have fast and very light jets. Light means that the composition at the beginning is essentially a Poynting flux that is converted in electron-positron pairs. So at the beginning, the content, the matter content of the jet is formed by pairs. But very soon, some matter from outside will entrain into the jet, and it will become slower and heavier. And when you have a high spin and high accretion rates, then you could have these extremely powerful jets, and you will have that are formed by the wind, that are slow and very, very massive, and you will have a spine in the middle of these jets formed by the faster plasma ejected by the black hole, probably by a Blandford-Snijek process. An example of this type of systems is SS433. This is the nebula that surrounds the binary system. The binary is located here. So the jets very soon become dark because electrons cool down, so you do not see the jet, but the jet continues propagating and producing these extended lobes that you see here when they interact with the interstellar medium. And some recollimation shocks appear at some points here where particles are reaccelerated and then they radiate synchrotron radiation up to X-rays and also gamma rays that have been detected. As I mentioned, this jets propagates through the interstellar medium, and at some point a bow shock will be formed at the termination point of the jet, where the jet interacts with external medium. So you will have a forward shock and a reverse shock. The reverse shock is expected to accelerate particles, and the overall morphology is very similar to that observed in radio galaxies, as I mentioned. This is one example, Cygnus X1. The binary system is located here. The jet points in this direction, and we do not see anything for several parsecs, but then we have the interaction of the cold jet with the interstellar medium that produce this bow shock you see here. This is thermal X-ray emission that has been detected with Chandra. An outstanding example of these effects is this remarkable microquasar, S26. It's not in our galaxy, but it's an extremely super Eddington accretor. The power of the jets is huge. It is estimated to be of the order of 5 times 10 to the 40 erg per second, just in the jets. And it is located in the Sculptor galaxy, located at 3.9 megaparsecs away. And this is the morphology of the jet as observed by the Australia Telescope Compact Array. It can be seen from the southern hemisphere. And the size of the system, the length of the cocoon, let's call the cocoon to the structure created in the interstellar medium, is of the order of 300 parsecs. So it's really huge. And there is a hot spot that produces X-rays, thermal X-rays from this part. And this is non-thermal emission, synchrotron radiation detected in radio, that probably is due to electrons reaccelerated by the reverse shock. And you have also thermal radiation from the center of the system that is compatible with a super accreting source, but that is seen edge on. So you do not see an ultraluminous X-ray source. Actually, this is underluminous for the power of the jet. So if you infer the accretion power just from the X-ray luminosity, you will see that it's of the order of 10 to the 36 erg per second, but the jets are 4 orders of magnitude stronger than that. So this means that we are not seeing the entire thing. And very recently, with my student Leandro Avaroa and other students, we have calculated the spectral energy distribution of this thing, and we concluded that it's capable to accelerate protons at the terminal region of the jets up to energies of beta electron volts, 10 to the 15 electron volts. So this is a PeVatron, a machine in the sky that is capable to accelerate protons up to energies close to the knee in the cosmic ray spectrum. And another interesting thing about these microquasars is that they have been detected in gamma rays, the most energetic form of electromagnetic radiation. For instance, Cygnus X3 was detected by Fermi, the satellite, Agile, the Italian satellite, flares, sporadic detections, but also detection that is modulated with the orbital period, which is very short for this system. It's of the order of 4.8 hours. The donor star is a Wolf-Rayet star. So the black hole is orbiting almost inside the atmosphere of the star. Very interesting object. As I mentioned, there were reports in the 80s about PeV emission in gamma rays, but at the time no one believed that. Then we have Cygnus X1, perhaps the most studied microquasar. It was observed by Fermi in correlation with the HAR state, the ADAF state. And also there is some hints of orbital modulation for this object. Agile have detected day-scale flares, and MAGIC also faster flares. And then there is a likely detection of this other microquasar, the 404 Cygni by Fermi. And then we have the superluminal microquasar, 1915, probably detected by Higra, the first stereoscopic operational Cherenkov telescope in Canary Islands. This was in the 90s. And SS433 has been detected by many instruments. Fermi, Hess, Hawk. Amazingly, Hawk detected the source up to energies of the order of 100 TeV. If you have gamma rays of 100 TeV, this means that the particles that are producing that radiation should be at the range of peta-electron volts, PeVs. And this source, SS433, has been resolved. So we know the structure in gamma rays. It's an elongated source in gamma rays. And then we have this amazing source, B4641 Sagittarius, that was detected by Hawk, this water churn tanks in Mexico. And it was detected up to energies of 200 TeV. So this is also a PeVatron. And this is the image of this microquasar. You see an elongated structure. Okay. But in the last 2 years, new detections appeared by this amazing instrument. It's a Chinese detector. It's a compound of detectors, actually, and it is called the Large High Altitude Air Shower Observatory. It's located in Tibet, and it is formed by huge water Cherenkov tanks with photomultipliers, and then a lot of more than 1,000 underground Cherenkov tanks for muon detection, and also scintillation detectors for electrons on the surface, and also there are atmospheric Cherenkov telescope for the radiation produced, Cherenkov radiation produced by the shower in the atmosphere. So this is an extremely powerful instrument that is now being improved. More optical telescope will be added. And 2 years ago, it published the first catalog with 90 sources. And of these 90 sources, 43 were detected at energies above 100 TeV. And what is interesting for us is that among these detections, there are several microquasars. Actually, the most energetic sources are microquasars. So 6 of them have been detected by LHAASO so far, and they are SS433, V4641, GRS 1915, then another one that is called MAXI 1820, and Cygnus X1 and Cygnus X3. These are the images of all these sources. In the case of SS433, the source is resolved, and these are cuts at 3 different energy bands. This one is at energies above 100 TeV, extremely high energy photons. Then we have here medium range between 25 and 100 TeV and 125 TeV. And you clearly see a structure with 2 lobes of emission. And then this one here is, I think this is for MAXI. No, this is Cygnus X3, sorry, Cygnus X3. This is MAXI, Cygnus X1, GRS, and this other one, which is, yeah, this one, Sagittarius, V4641 Sagittarius. And these are the spectra that are observed. You can see the most interesting case is Cygnus X3. They devoted an entire paper to this source because the spectrum extends well beyond 1,000 TeV. So it's a super PeVatron. It can accelerate particles at energies of the order of 10 PeV, beyond the need of the cosmic ray spectrum. This is amazing. Okay, but a mystery remains. Several mysteries remain. But the main one is that there are other PeVatrons in the catalog that are not identified with microquasars. They are not identified with anything. There is no detectable counterpart of this source. So what are these sources? Well, my proposal here is that if we now have a lot of microquasars already detected, in the past we also had many microquasars that had similar power to these ones. But these microquasars at some point were unable to continue ejecting jets, and they were transformed into what we call a microquasar remnant. So this is a new concept that I want to introduce. At some point, the donor star will stop feeding the black hole with matter. There are several reasons for that. For instance, if you have a supercritical system, the disk will have a strong wind, and this wind will interact with the star and can strip away the atmosphere of the star, so this could stop the accretion. Or, for example, the system could become detached, or the companion star, the donor star, if it is a very massive star, could implode directly into a black hole, so the final result will be just a binary system of black holes. We have also the possibility of supernova explosion of the companion and other possibilities. So this microquasar, the active phase where the jet is produced, is expected to last around 100,000 years, but no more. So what happened after that period of time? This is the question that I want to answer. So while the microquasar is active, essentially we will have continuous injection of energy in the interstellar medium by these jets, these powerful jets. And the evolution of the cocoon will be similar to the evolution of the cocoon of extragalactic radio sources. So you can follow, for instance, the standard model by Kaiser Alexander, and the expansion is expected to be adiabatic of the cocoon, and with weak dependence on the ratio of the power of the jets and the density of the interstellar medium. Then when the microquasar switch off, the jets disappear, the injection stops, and then the evolution continues as adiabatic expansion from the final state of the previous period. And after a while, perhaps 500,000 years, the matter that is swept by this expanding cocoon is so much that it starts to affect the dynamics seriously. We enter as in a supernova remnant in the radiative phase, and there is a final break of the shell, and then the whole thing disappears. So this is the evolution of a cocoon. This is time in years, and when the color switches to blue, it means that the jets are turned off. And then only the adiabatic expansion continues. Up to a final size, in this example, with an injection of this value of the order of 100 parsecs in 500,000 years. Okay. During the time that the microquasar is active, we expect also active particle acceleration at the terminal region of the jet. There we will have systems of shocks in the interaction region with the interstellar medium. We'll have a reverse shock in the jet, where this shock will be adiabatic and will be capable for acceleration of both electrons and protons up to high energies, as we see in some of the microquasars that are active today. Then from this active region, protons can escape and diffuse into the cocoon. So we can calculate the diffusion of the cosmic rays that are accelerated into the cocoon, solving the transport equation for an injection that stops when the jets are turned off. So essentially we did that, and what I am now showing you is the evolution of the proton distribution inside the cocoon after this diffusion. Here I am assuming a bomb-like diffusion. This means a few times, 5 times the Bohm diffusion coefficient. Later I will show you other diffusion regimes. But what is interesting here is that at the beginning, while the jets are active, the number of protons increases inside the cocoon. But then when the jets are turned off, well, the escape, which is the dominant loss for the electrons, because proton-proton interactions are very slow in cooling the protons, the maximum energy decreases inside the cocoon. And this is because the most energetic particles are escaping into the interstellar medium. And this is the same for the electrons. So this is the active part of the microquasar. So here the spectrum increases up to this value, and then in the blue part the electrons start to cool. Here cooling is important because of synchrotron radiation, because of inverse Compton upscattering of ambient photons. Okay, and what about these protons that escape from the cocoon, that diffuse out of the cocoon? This is the spectrum of protons that you can observe at 100 parsecs from one of these microquasar remnants. This is for Kragman energy dependency in the diffusion coefficient, that is what is standardly assumed for the interstellar medium. So you see that the most energetic protons arrive first, is this curve here, and as time goes by, the spectrum moves towards lower energies, because the most energetic protons escape from the cocoon first, and then the other ones follow. So if you have a cloud, these protons will interact with the cloud and will produce gamma rays through proton-proton interactions with the material in the cloud. So we have calculated the result of these interactions for different cases. One case is when the cloud is inside the cocoon, because the cocoon is so big that some clouds could be inside the cocoon. And then we calculated for clouds that are at 100 parsecs from the cocoon. And the results are something like this. The density of the cloud is of the order of 10 to the average density, 10 to the 3 particles per cubic centimeter. The cloud is rather compact, 1 cubic parsec. Magnetic field in the cloud is assumed to be 10 to the minus 4. And this is for a microquasar located at 5 kiloparsecs from the Earth. So this is the spectral energy distribution for the cloud inside the cocoon due to just proton-proton interactions. This is the contribution to gamma rays from these proton interactions. And this is synchrotron radiation by secondary pairs producing the same interactions. And this is relativistic bremsstrahlung produced by the same population of electron-proton pairs. And if now we move away from the cocoon and we look at the cloud at 100 parsecs, we expect something like this. Of course, it will evolve with time. So this is time in years. So from here to here, we have 500,000 years, and you see how the spectrum, as time goes by, shift to lower and lower energies and less total power in the cloud. Nevertheless, this is clearly detected by LHAASO, by Fermi, and also by SWIGO in the future. With these exposure times, 10 years for Fermi, 5 years for SWIGO, and 1 year, just 1 year for LHAASO. So our proposal is that some of the unidentified sources for which we do not observe other counterpart than a cloud, molecular cloud, for instance, but there is no apparent accelerator, could be the result of the irradiation of the cloud by protons coming from this reservoir of protons in the cocoon. And, well, a few words about non-Bohmian diffusion inside the microquasar remnant. The turbulence level could be strong, so assuming bond-like diffusion could be wrong for the interior of the cocoon. So we have considered different cases. This illustrates the case of Kolmogorov spectrum, so a spectrum with an energy dependence with an index of 1/3. And this is the evolution of the protons inside the cocoon. And this is the protons that reach at different times the cloud at 100 parsecs. And these are the spectral energy distributions for the cloud inside the microquasar remnant and for the cloud at 100 parsecs. You see that in both cases you have clear detections as well. And what about the primary electrons? Can we detect the cocoon at radio or X-rays? Because the primary electrons, as we saw in the distributions of the particles, were cooling through synchrotron radiation and inverse Compton radiation. Well, this is our estimate of how the primary electronic component evolves. This is the synchrotron radiation from the cocoon, primary particles now, and this is the inverse Compton. And the problem is that these are large structures in the sky, and the surface brightness at 1.4 gigahertz, for instance, are very, very low. So if you have one of these structures, it is very difficult to detect them above the radio noise produced by the galactic cosmic ray, electronic cosmic ray component. So there is diffuse synchrotron radiation in the galaxy. So if you want to detect one of these things, you need to apply some background removing radiation larger than some scale from your observations. So we are trying to do that right now in the direction of some of these sources in an attempt to detect the first microquasar remnant. Okay, so summing up, these are the points that I want to emphasize. We know for sure that microquasars are capable to accelerate particles up to and even well beyond PeV energies. This is a fact shown by, proved by LHAASO in the last 2 years. And most of the sources that have been detected are super Eddington sources. For instance, SS433, Cygnus X3, V4641 Sagittarius. So all these sources are potential super PeVatrons. They are probably accelerating particles, perhaps well beyond the knee of the cosmic ray spectrum. So this means that perhaps most of the emission between 10 to the 15 and let's say little before 10 to the 17 could be galactic and coming from microquasars. Active microquasars or microquasar remnants, that is our proposal. So this microquasar remnants, contrary to the active microquasars, could be dark PeVatrons. Dark in the sense that there is no electromagnetic counterpart that is easy to detect. So they would appear as these unidentified PeVatrons that are present in the LHAASO catalog. And this microquasar remnants might dominate the cosmic ray spectrum around the knee. And the cosmic ray production rate above 3 PeV is not extremely demanding from an energetic point of view. We are not talking anymore of 10 to the 40, 41 erg per second in cosmic rays as in PeV energies, but we are talking about less, 10 to the 38, 10 to the 39 erg per second. And we have seen that the energetic of these supercritical microquasars is more than enough to account for that from an energetic point of view. And an additional contribution could be from sources that go undetected because they are misaligned ultraluminous X-ray sources. So there is another line of research that I am pursuing with my students, studying how you can accelerate particles in ultraluminous X-ray sources. Apparently, since the radiation field is so strong, it seems not to be a very friendly site for particle acceleration, but there are some ways around this problem. The production mechanism will be not proton-proton interaction, but proton-photon interaction in this case. Okay, I think that's it, and I thank you very much for your attention. I am open for your questions.
Thank you. Thank you very much, Gustavo. I don't know, can you hear me through the microphone? I don't know. Okay. We have some questions.
Gustavo,
Sí.
Nice talk. I have a couple of questions, if I may, if
Please.
Maria Victoria allows me. One question regards on the population, right? Because as you know, there are several candidates for the PeVatrons and the LHAASO sources, right? Embedded sources like the blowing of massive stars, you know, the supernovae, a super bubble that could be produced inside young massive stellar clusters, or besides microquasars and massive stars, individual massive stars, winds as well, several embedded sources, right? So these are potential candidates and also reliable. Discussing about populations, you know, what would be the most interesting or most probable candidate? Have you done any, you know, preliminary population study for claiming that, okay, maybe microquasars are the main PeVatron source candidates?
Yes, you have mentioned a few potential candidates. In the case of supernova remnants, typical supernova remnants, we know even with strong magnetic field amplification cannot reach super PeVatron energies.
Yeah, not
but
individual ones.
Yes, I know. But if you have a very young one expanding in a bubble on very specific condition, okay, it could be the case. So the question is how many of these things we have in the galaxy?
Yeah, young stellar
well,
massive
this is
cluster.
just speculative because we do not know. instead, in the case of microquasars, we already know 25 of them in the galaxy, and if we have now 25 in the galaxy, and the lifetime of this object, the remnants, is 500,000 years, we should have perhaps a couple of hundred of remnants in the galaxy. So the energetic is far more important than in the case of supernova. Then you have OB association, collective effects, but there are many uncertainties because there are also a lot of effects that are usually simplified but could make efficiency of the acceleration not so powerful in this system. So a lot of things remain to be clarified in the case of OB association. It was proposed long ago by Romero, you remember, in '79. Then we have the pulsar wind nebula that are strong candidates,
as well.
but there also you have problems of radiative cooling that could be very important. So I think it's a competition between this and those, and I think what will be decided finally will be the detection or not of microquasar remnants, the real one. So,
Right.
So this will require extended radio observation. So it's not possible just to make a point observation with an interferometer. You need to make a mosaic of the sky, and so it's not easy. So far it has been done just for SS433, this famous Dubner and co-workers paper from 1998. It took a lot of time, so it's not an easy task.
Yeah,
but,
I think with the astronomy array, we are going to get a lot of.
Well, yeah, Meerkat, and okay. So the future looks
the TV counterpart, at least.
The future looks
to identify the sources, LHAASO sources, and see, right?
The future looks promising about the tools we have to give a final answer to your question.
Right.
So from an energetic point of view, I am very happy with microquasars so far.
Yeah, it's a reliable one. One of them.
No, I do not say that is not the case.
But yeah, definitely you are correct. Can I make the second question? Okay. Okay. So the other question is one of the sources that you presented in the beginning, this S2 source that you built, the
S2026. Yes.
Yeah, I noticed that you get a high peak TVs, right?
This one.
But why? But I see no observation for this, right?
Because it's below the sensitivity, because it's located in the galaxy.
But this part is under the sensitivity because it's 12,
here,
right?
Here you have
TV.
Fermi sensitivity curve. You have LHAASO,
TV, but
and CTA. Even.
Why not with MAGIC and?
Because the sensitivity is even worse.
Because
than
it is still small enough. Okay, for CTA.
Remember that.
Okay, so it's very small.
It is located megaparsecs away.
Yeah, I didn't realize that
in this galaxy. It's amazing that we can see it at radio so well, and we can resolve this force being in other galaxies. This is because it's extremely large and very powerful.
So yeah, it's still under the sensitivity. I didn't realize that.
Yes, sorry. Perhaps the set
I thought that
I
only saw the lower ones.
Yeah.
But the dashed black one, what is that one?
This is what would happen if we move this object into our galaxy.
Okay.
So in our galaxy, it will be visible.
Right.
Very easy to detect it. But
see.
Unfortunately, it is in our other galaxy.
Okay. Thank you for the clarification.
I'm curious to know if there is any place or any region in the cocoon where you can observe hydrogen-stimulated lines that would map the velocity very precisely.
Well, lines are observed in active microquasars because matter is transported by the jets, so you can measure the velocity of the jets, just measuring the lines. For instance, that is the case of SS433. Iron lines are detected, and so you see how the red shift and the blue shift lines indicates the orientation of the jets, and we know because of this that there is a hadronic contents in the jets of SF433. In the other objects, it has been not so easy to measure these lines, but in principle is possible, of course.
Okay.
You need to observe, I think, with New Star, no? Or perhaps with Chandra, perhaps with Chandra as well, No, Chandra no, with XMM is better for spectra.
Yes, and with the Chandra spectrograph as well.
Yes, sorry, my mistake.
Okay, thank you.
Welcome.
Very nice, Gustavo. I have two questions, if I may.
Yeah, please.
For one, this is already exactly the right picture, right? So you showed this one spectrum for a compact cloud of high density somewhere there, right?
No, here in this particular case, this is the emission that is coming just from what we observed, the active radio lobes in the active phase of the microquasar. We have not included additionally here.
But I mean, on some other slide, you had a cloud somewhere, and then you showed spectra for that.
Yeah, I know. Yes.
Okay.
Yeah.
So the question that I really have is that this cloud was relatively compact, was a parsec or so in diameter.
Yeah, here.
Which means if you place this at a distance of 100 parsecs, you have 1,000,000 times the volume, where you can also produce gamma ray emission. And then you have the dense ISM around the cocoon, where all particles need to go through, all of them, right?
Yeah.
Where you also produce tons of gamma ray emission. So the real question is, why don't we primarily see the outer cocoon?
Yes. The shell around the cocoon,
right.
yes. At the early stages of the evolution of the cocoon, the concentration of mass is not high enough to show up in gamma rays. But you are absolutely right about the later stages. So we are now working on a new paper that is on the visibility or detectability of these systems, where we analyze the contribution from the cocoon, and also we analyze the shell around the cocoon at every time, and we also take into account something that was not considered in this first analysis, that is second order acceleration by turbulence inside the cocoon, something that perhaps on very large scales could contribute to modify somehow the spectrum we are predicting.
Yeah, concerning the spectrum, I noticed that the proton and therefore also gamma ray spectra that you showed in your model typically had a kink at about a TeV or a few TeV, and I was wondering where that came from.
Let's see.
There, for example.
This is electrons. Let me see. Sorry.
Okay, so there you already have, maybe this is a few tens of TeV. There's already a kink. Basically right from the beginning.
Yeah, you say
that
here.
One. Yeah.
So what is the question? Sorry.
Where does that come from?
The break. This break. I think that this is a effect of the escape is strong till this part, and these particles still do not have any chance to escape. I think it's produced by the escape, not the cooling, because the cooling is not important.
No, cooling not. So that means you had Bohm diffusion, right? You have energy dependent escape.
Yes, exactly. We consider several possibilities: Bohm-like diffusion, and inside the cocoon, and then Kolmogorov, and even Krachmann. So this is the most optimistic case with Bohm-like, and the less optimistic case is with Kolmogorov. Yes.
Right.
Yeah.
Okay. Why is that so?
Sorry.
Why is that so? Because
because of the energy dependence. So in this case, protons escape faster the more energetic ones.
In this case, right? Yeah. So the other way around. Yeah,
Yeah,
okay.
yeah.
Mhm.
Yeah.
I agree.
I was done.
Okay, thank you. Do you have more questions? We have a repeated question, so we drop out. So I think it's time for a coffee break,
Okay.
and we can. Okay, we have it back.
A bit in this. Thanks for the talk. But in the sense, like we were discussing now, like in the last few years, we had some advances, theoretical advances discussing like mirror diffusion. There are some other models trying to explain like the confinement of the cosmic rays. Like okay, like usually. If you look, for instance, in young massive stellar clusters, there's like a range of energies, like you have a degeneracy of the parameters. Mirror diffusion, for instance, can explain some gamma ray observations that with an injection energy like close to E2 minus 2, while usually people use E2 minus 2.7 and use bomb. So in this case specifically, but like for these kind of sources, what kind of energy injection are you expecting? What kind of physics for the acceleration of particles?
For the acceleration is bond diffusion, the standard Fermi acceleration, with some enhancement of the magnetic field by typical amplification mechanisms. But that is the source of the cosmic rays while the system is active. When it's turned off, then we have just the evolving population of protons in the cocoon. They are perhaps, as I mentioned to Martin, perhaps it could be important Fermi type 2, reacceleration of the particles if the medium is quite turbulent, as it is suspected to occur, for instance, in the radial lobes of Centaurus A or external galaxies. But you are right in the sense that there are a lot of different possibilities that deserve study. This is the very first paper in a new field because it's the first time that this type of objects are proposed. And there are a lot of things to do, for sure. We are aware of that.
Yeah. I think it's the next slide that you showed some of the proton spectra.
These are electrons. Sorry.
The other one that has the different dependencies with energies show like Kolmogorov, Kreisman.
This is protons. Sorry.
The diffusions.
This one.
This one and the next one. So the other one is also E2 2.75. Like just to understand like the unities and what kind of spectrum you get in your first modeling.
This is what happens to the escaping proton distribution after traveling 100 parsecs, assuming for the interstellar medium a Krachmann energy-dependent diffusion coefficient that discuss this normalization.
I was just asking, like the next, right after this one, you show another one?
Yeah, these are spectral energy distributions.
I think it's then the next, just a few more slides.
This one?
Yeah, this one. It's because it's small. Like you're doing the same normalization, but just changing the, like because we can't. I can't see the.
In this case, in order to calculate the diffusion coefficient, in these cases, we consider some level of turbulence that is an assumption. It can be changed. It will not affect too much. We are considering that level of turbulence is of the order of 30%.
Okay.
So then, well, this is the size of the cocoon. This is the Larmor radius. Okay, and then you have the exponent in the in the energy.
Okay.
So we use that expression.
Okay, thanks. It's just because the plot down there is a little bit small, and I was just like checking if it
this
like
one.
Yes.
Yeah.
It's the same as the other one. You
no,
just
it's not the
same.
It's different. But
yeah, like you're changing the modeling, but the
yes.
plots, the rest is the same.
Yes,
just
exactly.
that I was clarifying. Thank you.
Yeah, welcome.
Okay, so everybody asked a lot of questions, so I will ask my question, Gustavo.
Please.
Among the LHAASO sources that do not have a clear counterpart, there are many of them, and they have their own distribution and their uncertainty box in the sky. Are there some favorite cases that you would like to look into? For example, for seeking the radio hints there, or
not yet, because first we want to have our paper on the detectability at all wavelengths of the cocoon, taking into account these complications that we were discussing with Martin. And after that, after knowing what we are looking for, we will start to select the sources. And in addition, the second catalog will appear soon, so there is no point to start with the first one. So they are producing data at an amazing rate, so it's worth it to wait just a few months.
Yeah, I agree. Okay, thank you very much. More questions? No? Well, I invite you, let's thank Gustavo again. Thank you very much. And I invite you all to discuss with Gustavo at the coffee break. Thank you.
Muito obrigado.